Thank you very much for holding on, and welcome to the webinar for today. As I said, I'm Pia Prohaska. I've been 30 years in the field, and I've mainly worked with optimizing and design and commission of municipal wastewater treatment plants. The topic for today will be how to improve treatment by upgrading your ditch and how to increase capacity of an existing ditch. The agenda for today's webinar will be a short introduction to Veolia's ditch technologies, and I will get into some of the key benefits for these processes. Then I will talk a little bit about a recent project that we worked with Hazen and Sawyer, where we were able to increase the capacity on a wastewater treatment plant without adding any additional volume. And the last topic will be an introduction to Veolia's more advanced online control system that can be used both for optimizing of O&M costs, but also in the light of this topic's title, we'll be able to expand and intensify the capacity of a existing wastewater treatment plant. In regard to questions, you are more than welcome to ask questions as long as away. We are, of course, a little bit behind the schedule, but the questions will always be more than welcome. So Kruger came to the American market in the late 80s, and our main product at that time was our ditch systems. We do have more than 100 installations here in the United States, and the size of them, and the majority of those will be a size range in 1, 2 to 5 MGD. We also do have some larger plants. Over 50% of these installations is with our unique biodinitrous system, and that is operates slightly different from the more traditional ditch systems. As I have worked 30 years in the field for Kruger, I worked first in Denmark, and then I worked here since 2009. I worked in the United States. I personally have more than 30 years experience of applying this technology and using it. So first I will use a short time of kind of go through what is a biodinitrous system and what is the main difference between the more traditional ditch systems that is on the market today. The picture here that you see here is a layout of a traditional system where the biodinitro is in a ditch, is being done in ditches, and the source of aeration will be rotors. It's important for me to mention that this process is not tied completely to rotors. We have done them in round tank, rectangular tanks. We have done them with the jet aeration, and lately very much we do them with diffused air. One of the main difference of this system is that in traditional ditch system, you will typically have each of the reactors will operate parallel to the other reactors. But in a biodinitrous system, they actually operate in series. So you will have some sort of distribution equipment where you are able to introduce all the wastewater, all the influent, and all the rest to one reactor. And then you will have connection either with a hole or pipes going into the second reactor being treated here, and then you will have the effluent leaving the second reactor after it's been treated. That can either go to a secondary anoxic zone reaeration, or it can go directly to secondary clarifiers. These systems runs on a time-based cycle. And the cycle time is normally 3 hours. So half of that cycle, that would say 90 minutes, you will have influent going into the first reactor, going through this hole into the second reactor, and out here. Then after those 90 minutes, you will have the flow direction reversed, and it will go into the other reactor, go through this hole and out of this reactor. the ability, when you have two reactors operating in series, it is very easy to obtain both a low TN in the effluent as well as a low ammonia in the effluent at the same time, because you can have denitrification happening here, and then you will always have nitrification happening in the last reactor to ensure that you constantly have a low ammonia going to the effluent. The other feature is that there is no internal mixed liquor recycled pumps, because you have this variation of nitrate and ammonia going up. The concentration will go up and down in each of the reactors depending on what processing. The ammonia will go down and the nitrate will go up, or if it's denitrification, then the produced nitrate will be reduced and go down during that phase, and you will but the ammonia that you will have in the influent at this one will make the ammonia concentration go up. There is a complete separation of mixing and aeration, and the system had unlimited aeration turn down. So one of the absolutely best features or benefits of this system is that it is highly flexible. So you are able, and which for me as a process engineer makes my life very easy. So this system is actually able to operate, like for instance, when you go out and commission a plant and you have to introduce nitrification, you can simply turn the aeration capacity on fully in both reactors, and you will have 100% aeration there. And you will build up your ammonia. And as soon as the ammonia is starting to be reduced, and you know that your nitrification is happening, then you can start introducing some denitrification. And depending on the load compared to the actually design capacity of the plant, you can kind of move and get more and more denitrification, better wastewater, effluent quality, until you kind of reach a limit where the ammonia starts getting in the composite sample. You can see that the ammonia, you have some ammonia in the composite sample, which means that in real life, you can actually move between 100% nitrification. And I have personally operated a plant all the way down to 30% nitrification. That was very unusual because this plant was designed, you know how it is, with normal wastewater, 250 milligrams of BUD, a TKN of 40, and everything should be fine. And it should have like 75% nitrification, 25% denitrification. But when we came out there, it turns out that most of that wastewater was just septic tank sludge, and there was really no BUD there. So in order to meet the effluent requirement that was at 3 milligram per liter without any external carbon, I had to move my objective or the ratio between nitrification and denitrification down to 30%, 70%. So this plant has been operation I think since 2010, and meet a TN less than 3 milligram without any external carbon and addition, and basically no BUD in the wastewater. So basically, most of the carbon comes from fermentation or producing of internal carbon of the TSS that comes in. So this flexibility also makes this system a perfect candidate when you want to introduce online control. As I said, we had a recent project here in North Carolina. It was the city of Cary, and the city of Cary, or the whole area here around Raleigh, is very much in expansion. There's a lot of people moving in here. We have company coming, so there is constantly growth, constantly being built new buildings or houses. So the wastewater treatment plant knew that at some point they would have to increase the capacity of their wastewater treatment plant. As of now, and during the construction, before the construction started, they were only operating 2 out of the 3 trains. You can see the 3 biodynither trains here. You can see that they are the traditional ditches, and we They wanted to start this project of me that the load to the plants capacity during the construction. It would be very beneficial that they could work on one train while operating the other two and still meet the effluent demands of the plant. So the primary goal of the project was to expand or to increase the capacity for 12 MGD up to 15 MGD without adding any additional process volume and still meeting the very stringent effluent demands that this plant has. They do have a yearly amount of total nitrogen that they like pounds per pounds TN per year. And with the new expansion with the 15 MGD, that equals out to less than a TN less than 3, actually a TN less than 2.7 in the effluent. TP was 1, and they still had to meet an ammonia less than 0.5. The other thing that was with this plant was that they have for years operated this plant without absolutely no addition of any chemicals. It was a short period of time they would add some ferric to keep the phosphor down when the biological phosphor treatment kind of went out of whack. But in general, they really did. They expect to operate this plant, meet the effluent requirements, increase the capacity, and still don't use any chemicals for the treatment. So, so the volume for the expansion from 12 to 15 MGD was there. Well, you should use that volume at this maximum all the time, the maximal way, the duration capacity. It was very normal during higher during the diurnal high loads that the plant was not able to meet the DO set point of 2, and they will operate down 0.5 to 1 milligram per liter. So we need to do something. So what they did was they did install a new blower station, and they used centrifugal blowers. These are not the most energy efficient blowers, but unfortunately the city had some not so good experiences with with turbo blowers, and they're turned down. So they were very adamant that they wanted to use these kind of blowers. Then we also installed ammonia and nitrate analyzers in the ditches, and we replaced the existing PLC control with a new one where we added, instead of just being able to do a time-based control, like as I mentioned, 90 minutes cycle, 3-hour cycle, 90 minutes there and 90 minutes in the other flow direction. We did a real-time PLC online control that would be able to change the phases, length of the phases, the process conditions in the different reactors at any given time, and also use the ammonia for ammonia-based DO control. So the result of this one was at the same hydraulic or organic load as before we did this project. We had the same load here. We were still only operating 2 out of the 3 trains. What we have seen so far is a reduction of the overall energy use of 5 to 6%. Of was before the project. You have to remember this is kind of a combination of changing aeration equipment from rotors to diffused air, and the diffused air should be slightly more efficient than the rotors, because the site water depth of these ditches was 18 feet, so we could use the air fairly efficient. But it's also a combination of online control where we are constantly changing how much time we're denitrifying and how much time we're nitrifying. So we did decrease the time we were nitrifying and increase the time we were denitrifying. I believe that we could have gotten a lot more energy savings if we had had the right blowers. We also had the smallest blower that we had. The turn down of that one was not enough for us to actually meet a DO of less than 2 during low load phases. And even with a blow, we also had a blow off valve. So the whole blower station layout was not really meant for energy savings, and that was also not the primary goal of the project. The average effluent before and after is shown here. You can see the TN is in the same range, and so is the total phosphor, maybe slightly better after than before, but I did this table totally wrong. I'm sorry. I just realized before. So before we had a TN of 1.95, and then it went down to 1.73, and after it was the TN, the TP went from 0.34 down to 0.24. I'm sorry about that. So the last topic of this one is an introduction. Last topic of the one is our more advanced online control system. It's called Hub Grade Performance Plant, and this has we have been doing this for many years. As I said, I came to the U.S. and started working in 2009. But I have worked with this online control program since the late 90s. So, and that was my main focus when I worked in Denmark, was to implement these online optimization system on wastewater treatment plants for different reasons. It could be optimization of the OPEX, or very often it would also to increase the capacity of an existing wastewater treatment plant. So as you can see, we have more than 100 different installations around the world. The majority of those is in Denmark, and I worked with most of these installations over the years. It was kind of interesting for me when I moved to the US, because one of the first thing I did was I was reading this report from the EPA about online control, how to implement it, how to do it in the US. And this report, I think, came out in 2009. And when you went to the list of reference and the system that they talked about, I would say more than 50% of that was actually this system. And so it was recognized that we have done it for a while with good results. So why do you do advanced optimization? So what I see here in the United States is that the goal when you introduce online control of a system, it's very often in order to reduce the OPEX, the O&M cost. We install a nitrate probe, so we know how much external carbon we should add and when we should add it. We do the same thing for precipitation, and to some extent we do it to save energies during aeration by controlling the DO based on ammonia. That is all related to savings in the O&M. But what I don't see that much here is that you actually use the online control to optimize the actual process. So before you even start wanting to add any of these chemicals, you try to optimize the process as much as possible so you can reduce the amount that it will be necessary, and also in some cases be able to eliminate it altogether. So in all these plants that we have introduced this online control, we have been able to. We can also increase like the hydraulic capacity. So, for instance, we can operate the plant and we can introduce some settling zones actually in the process, and being able to handle a lot more hydraulic flow through peak flow conditions, like peak hour conditions, get more flow through the clarifiers because they're not seeing the same solid loads than they would see normally, um, because we have changed the process conditions in the actual biological section. That way, we can reduce overflow and bypasses, and also we have had really good experience with reducing the cost, or even have to introduce more equalization tanks or holding tanks out in the sewage system. Carrie I talked about, this plant was not the most advanced control. This was only based on PLC control, but we were still able there to increase the capacity with up to 25% by introducing an online control. And we have used that in multiple plants where the plant has been fully loaded to the design capacity. And by introducing this online control, we are able to use every piece of, or every corner of the volume the most optimal way, and actually be able to increase the treatment capacity and still meeting the effluent quality. This system also has ability to incorporate a control of the whole sewer system. So we can actually also look at the sewer system and the wastewater system as a combined system, and thereby, again, protect the wastewater treatment plants for high peak loads of water by using the sewage system sometimes to store some of the wastewater there during peak hour flows, and sometimes to direct the wastewater in different directions. As secondary benefits of this online control system is, and which is super important, is that it gives the operator much larger insight in the biological process and much bigger understanding, which also leads to a better operation of the plant, and actually a more fun job, I would say. One of the other things I want to mention is that the system is also right now, we are very much focused on reducing footprints, carbon, like greenhouse gases footprint of a wastewater treatment plant. That is both of reducing the chemicals, of course. It's also reducing the energy that we use for aeration and mixing. But very important, and we have about, I think, 4 plants right now that has actually monitor. They actually monitor the emission of the N2O, which is a very potent greenhouse gas, and they actually control the plant, the aeration and the denitrification process conditions to minimize this emission of this very potent greenhouse gas. And that's definitely something that's very interesting for the future. So what do we typically achieve? What have we achieved when we look over all of those more than 100 installations that we have? Yeah, I mean, one of the low-hanging fruit is very often we see a huge reduction in the energy consumptions. We very often see aeration reduction from 10 to 30%. Of course, that all depend on what is the aeration capacity. How is the aeration equipment put together? And also, how well was the plant actually operating before we introduced, the online control system? We also do some reduction on the energy that we use for mixing. We have a module that will go in and evaluate if the mixer is on VFD, of course, if we could turn down the mixing intensity and use less energy for mixing during low load situations where we don't have the need for using the full amount of denitrification capacity that we do have. We also looked at the IMLA pumps. Very often the IMLA pumps is set to something always 300% of the influent flow, but sometimes it can be beneficial to reduce that because your pre-anoxic tank has already met its maximum capacity, and you have nitrate kind of bleeding through the pre-anoxic tank. So in that case, you can reduce the internal pumping, so you will always keep like a optimal concentration of nitrate in that pre-anoxic, which means that you basically need to be above 0.5 to 1 milligram per liter nitrate, leaving that pre-anoxic. Anything else will be excess pumping. The same way, and this is more like this is process optimization. So during the night, you may have extra capacity, even if you are running it at 300%. You basically have no nitrate going through to the oxic zones, and you can increase your inlet flow and get more denitrification and a better effluent results during the night, and thereby you're a little ahead when the plant hits its higher loads later in the day. We very often see a reduction of chemicals for pea precipitation somewhere between 20 to 100%. Again, it depends a lot about how was this controlled before. Was it time-based? Was it flow-based control? Did they have some kind of monitoring? But in general, pretty good results, which also leads me to external carbon. It is very, very often that we actually will be able to turn the dosing of external carbon off altogether for nitrogen removal. So all this less chemical addition will also lead to less sludge production, which is an added secondary bonus of the online control. We see a higher hydraulic biological capacity. As I said, we have seen 20 to 100% higher flow. That can be used to prevent wasting untreated wastewater, like in the harbor of Copenhagen, because the sewer system and the wastewater treatment plant now is an integrated and controlled combined. So we are using all the equalization tanks at the right. Which part of the city do we need to pump into the wastewater treatment plant? We prepare the wastewater treatment plant for a high peak hydraulic load. In the case of a bionitro process, we actually turn one of the reactors, the last reactor, we turn the mixing off, we turn the clarifier, so the TSS load to the actual clarifier is a lot less, and we are able to get this flow with a reasonable treatment through this high peak period. And as I said, in general, 10 to 40% more load if we put that on an existing plant. And of course, as we all know, that better, like online control, we always see a much more stable effluent quality. We also see very often a much improved effluent quality, and total nitrogen, we have seen 20 to 50% reduction in the total nitrogen coming out of a plant. And again, with very often less use of external carbon, and total phosphorus, BOD, and COD is about 0 to 50%. BOD and COD, very often we don't really see a lot of improvement. Total phosphorus, yes, to some extent, but very often the total phosphorus is more about saving chemicals for precipitation and still meet the same effluent quality. And then and then you have the other advantages, as I mentioned, that we have this ability to reduce the carbon footprint of a wastewater treatment plant, which is increasingly important in the world that we are moving in for today. So how does it work? So when you have a traditional control, the traditional PLC control, you would put your set points in a conservative in a conservative way. So you will always be able to meet the loads and meet the effluent criteria during different load situations. In this one, if this was a load through 1 or 2 days, you can see the plant operator manually adjusting some of these set points to kind of meeting the different loads that he will see throughout the day, based on experience or just based on flow or whatever means that he has to identify that you have these load variations. But he sets these criteria fairly conservative. So you would run with a DO of 2 or 1.5 and not vary that DO set point through the day, or only, based on experience. But with an online optimization, what you're able to is that every 5 minutes, or depending on your online equipment, you will receive updated value of nitrate, ammonia, and in some cases phosphate as well. So then the algorithm that you have in your online control will constantly adjust the set point so you follow the load as close as possible and still meet the effluent demands. So that's basically what it does for your system. One of the key module in this whole in this advanced control is what we call the DO and the nitrogen module, and it's focusing mainly on DO control and nitrogen removal. And what it does, that we will have ammonia nitrate analyzers in one of the ditches, potentially two, depending on the application. And what it's doing is that we are constantly trying to avoid over-aeration, and we are trying constantly to use the internal carbon, the BOD that is in the wastewater, and also the carbon that is produced through fermentation, through breakdown of the TSS and the bacteria in the system, constantly using that to balance the ratio between nitrification and denitrification processes compared to what the variation in loads is. So you can see down here in the right corner, this is a criteria function. And what it does is that based on the actual ammonia concentration and nitrate concentration in any given reactor, it will decide if it is best to stay in a nitrification mode, or if it will be most beneficial for the effluent to obtain the best effluent to switch to a denitrification mode. But as you all know, depending on the load, the goal of the control can kind of change. So for instance, if we are at a peak diurnal load, the ammonia will eventually go up. And our goal will be, if we have an ammonia limit, which we very often have here in the United States, will be to protect the ammonia, to protect the ammonia and ensure that we will not have too high ammonia in our wastewater treatment plant, in our effluent. So it will allow for more nitrification and we will have more nitrate going out. During this period, we will have longer nitrification phases, and we will have shorter denitrification phases. But sometimes, if we don't have an ammonia limit on the plant, and we have maybe a limit of 5 milligram per liter, it could be actually an advantage to allow a higher ammonia concentration to go out of the plant. And I'll get back to your questions. Yes. And so you can set your goals depending on how your effluent limits are set. If you have ammonia, you need to drive the ammonia down. That's what you protect, and you will just use whatever additional volume to improve your denitrification. If you don't have an ammonia, you are allowed to have a high ammonia, and you can use more volume because you don't have to nitrify all the way down, and you can use that volume to drive the nitrate down and then actually achieve a better total nitrogen. So it depends on your goals. And some of the questions I have here, I kind of want to skip over the laugh gather. It's there, so you know it, but we're a little short of time. One of the questions was, are we able to actually introduce BioP in a plant that is not born with anaerobic dedicated volume? And yes, we have done that. We have done that on multiple applications. Scenario. We don't need that much ammonia is probably basically zero or very low at that point. We have the nitrate is low, and basically we might even have too much volume there. So what we do is that we drive that anoxic zone, the anoxic condition, down to an anaerobic, so the nitrate is totally gone, and we introduce anaerobic periods during the day. And that way we can obtain biological P removal in these plants. And we have done it in different applications. We've done in MLE plants, we've done it in single ditch configuration, and we have definitely done it in our biodynitro system. So yes, we have done that. We have four so far. We have 4 or 5 plants where we do it, and we have had a 80% reduction of chemicals for precipitation by doing that. In this one, 70 here, 20 here, and we did the extension, so we could go from 750 to 1 million here by introducing this online control system, and that without any BioP tanks. I have here a couple of examples. This is doing a 5-month evaluation of this plant. We had, this is in euro, and I think at this moment the euro is basically equal to the US dollar. So and this is a fairly small plant. I would say this is like I would say a 6 million gallons per day plant, maybe 5. And we were able to save about $35,000 on energy cost, and specific energy consumption was reduced by 45%, and the daily kilowatt consumption was reduced with 30% on this one. This case study here, which is in Denmark, and this one is about, I would say, 10 million gallon, I'm thinking in person, system. Yes. Okay, I will come to these questions. So this is like one of our flagship ships, and I'm proud of it. This system started with this DO control nitrogen module, phase control. And this started, I think, 30 years ago, 25 years ago. And over the years, they have always been first of implementing all these new ideas. So right now they are controlling their sewage system. They are controlling their energy production, and when they're using energy based on when the energy price is low and high, they, as I said, combine optimization. They do the network optimization with the wastewater, and they have a weather predicted control. So when they watch the weather and system and the wastewater system for a peak load, a peak flow situation, while they are reducing operation cost in the wastewater and have been able to increase the hydraulic and the biological capacity without really, excuse me, um, adding any existing volume. I think this plant was built in the late 80s. Most of the plant in Denmark was built in the late 80s. Very few new plants have been built since. So a lot of the plants is very pushed for capacity and has used this system to do that. So that was the last. And I would like, so one of the questions that I see here is, let me see here. So this is any thoughts of how this process may perform for industrial wastewater application that have high TKNs with BUD that is so TKN BUD ratios that's much higher than typical municipal wastewater streams. How low design FM and how long sludge age. So yeah, I mean, we have definitely used these system on industrial wastewater systems. We have definitely used them where the majority of the load to the municipal wastewater treatment plant an SRT model that would measure the SRT in the system and will do an automatic waste based on the SRT. We will, but I mean, if you have a very high BUD TKN ratio, then you don't necessarily need to, and most of the TKN will actually be assimilated in the sludge, then, and you don't have as high need for denitrification, then that's not the most interesting module, but you still have the DO control. You can have, you can, oh, there's a lot of things. If we have, like based on industrial load to a municipal wastewater treatment plant, we will take trains in and out of operation to save energy and to help with that. The other question is if you are, and that I agree that is a problem. So the question is if you are not using methanol all the time, as I said, it's only sometimes, how do we keep the methanol population up? Or do you have any, or do you have to use another source of carbon? And yes, as we all know, you need to add methanol in order to keep the right bacteria in the loop. In that case, what you would probably do is you will go down to a minimum dose of the methanol in periods where you really don't need to use it if you feel that you do need to keep adding this methanol. We did have plants in the beginning when we introduced this system. One of the first plants was using methanol for carbon source. And it was easy to answer the question here because after we introduced it, they never used any external carbon source after that. And that was without any post-anoxic treatment. And yes, I know that I said that the bionitro system is very good for online control, but of all these plus 100 plants that we have implemented this system, the majority of them is not a bionitro system. We have done it in all kinds of MLE processes. We have done it in 5-stage Bodenfos. So yes, and other oxidation ditch systems. It's very easy to adapt to different process systems. So I am so sorry for all this if I'm going over time and all that disturbance in the beginning, and I hope I didn't yap at least one more minute, but so please let me know if there's other questions. And if you needed me to be more detailed with some of the things. that I have talked about.
I don't see any additional questions. And I believe you did reference or speak to Stephen Woodruff's question.
Yeah, the
Okay.
one with the how this system could adapt to an industrial application.
Yes,
Yeah,
absolutely.
yeah.
Absolutely.
I mean, every time we go in and we tried that, and we're going to implement this online control, advanced online control system. We have all these tools in our toolbox, and depending on the goals of the project, is it operation saving? Is it extended capacity? Is it hydraulic issues? What issue is an industrial component in that where the load goes up and down? So we pick and choose from this toolbox to create the best system for this plant. And you can also, depending on how many modules you are adding, get the system more or less optimized, because it's all about, in the end, it's all about how much money, how much do you want to invest in this system, and what is our goal. Of course, if you use online control and you avoid huge capex investment, that will kind of pay for the project itself. But it's also very easy because it's super easy to start with one or two of the modules, and then you can simply build on as time goes. As I mentioned, my last case in Colin, which I was Flagstiff, I mean, it started with one module, like the main module, and it has expanded. I don't know how many of the modules they're using. I know that they keep inventing new modules, new ways of seeing new possibilities on this plant, because it has so many options here, and so yes, there's endless ways of putting this together and use it. So I would like to, I don't think there's any other questions. I would very much, again, thank you for your patience.
Mhm.
It was really nice that you gave me. I had to go on the hotspot on my phone to get in, but we managed, and I'm very thankful that you stayed on this webinar. And if you have any questions in the future, you're more than welcome to contact
All right. Yeah, I think this was great. Your audio is cutting out just a little bit, Paya, but
for
again,
any
as you
questions. Sorry.
I was just saying that your audio is cutting out just a little bit. So I'm going to go ahead and um, thank everyone again for your patience, for hanging on with us as we work through some technical issues. We really appreciate it. But I will state that this does conclude today's e-showcase. I thank you all for attending. The recording will be available at wethbuyersguide.web.org. We will send all registrants an email tomorrow with that link. And please visit our event calendar to sign up for future webcasts.